بسم الله الرحمن الرحيم. In this lecture, we are going to speak about the solutions about ordinary points, where the solutions will be written in power series. Start with the definition. If we have the second order differential equation a2x y double prime plus a1x y prime plus a sub 0 x y equal to 0. We have this equation, and we divide by the leading coefficient, or the first term, which is a2. Then we will have the standard form. Y divided prime plus bxy prime plus q of x y equal to 0. And for this one, we can now define something called the ordinary point or the singular point. A point x equal to x sub 0 is said to be an ordinary point of the differential equation 1 if both coefficients b of x and q of x are analytic, or it means differentiable at x equal to x sub 0. If they are analytic, means differentiable, continuous at x sub 0, then we call it, that point is ordinary point. If these are not differentiable or not analytic, then p of x and q of x are, or the x sub 0, we call it singular point. So if it is not ordinary point, then we call it singular point. So we have ordinary points where p of x and q of x are analytic. We can say differentiable, continuous, and everything it is defined over this x sub 0, or at this point x sub 0. If it is not ordinary point, then we call it singular point. More generally, we can say that the number x sub or x equals x sub 0 is an ordinary point of 1 if a2 x sub 0 is not equal to 0. We go back to C. If the leading coefficient there, the first coefficient, if it is not equal to 0 at x sub 0, then x sub 0 is an ordinary point. If it is equal to 0, then we call it singular point. Because p of x, in other words, we can say it is a1 of x divided by a2x. So the denominator must not be equal to 0 for an ordinary point. Now we can think about the existence of power series solutions. If x equal to x sub 0 is an ordinary point of the differential equation 1, then we can always find two linearly independent solutions in the form of the power series centered at x sub 0. So we can find solution of this form. The power series sigma n equal to 0 to infinity c sub n multiplied by x minus x sub 0 to power n. So if x sub 0 is an ordinary point, then we can find two linearly independent solutions in the form of the power series. And the power series solution convergent at least on some interval defined by this relation. Absolute value of x minus x sub 0 less than r, where r is the distance from x sub 0 to the closest singular point. If we have singular point, we just find the closest distance between x sub 0 and the singular point. If we don't have singular point, then r will be from minus infinity, or the interval will be from minus infinity to plus infinity. So the solution of this form said to be a solution about the ordinary point. And the distance r is the minimum value or lower bound for the radius of convergence. So some examples. For that, we need to find two power series solution of the given differential equation about the ordinary point x equal to 0. this is my ordinary point, x equal to 0. It means I need to find this form, Cn x to power n. Because it's x minus x sub 0, but x sub 0 is equal to 0, so I need to find it in this form, x sub n, x to power n. So to find this, the two solutions, we will assume that y will be in this form. Cn x to power n. And we know that the second derivative for this one can be written as n multiplied by n minus 1 x to power n minus 2. So I have c there, c sub 0 or c sub n. And n from this time, because for the second derivative we start from 2 to infinity. So this will be the second derivative, and this will be the form of y. It is c sub n x to the power n. So if we plug these two form in the equation, I will have second derivative is written as sigma of Cn times n multiplied by n minus 1 x to the power n minus 2. And n start from 2 to infinity. Plus y, which is sigma n start from 0 to infinity, Cn x to the power n equal to 0. Now I need to combine the two series, but I have the powers are not the same. Also, the indexes n starts from 2 and n starts from the 0 for the second series. So I have to unify the two indexes and also the powers. For the first one series, I will let k equal to n minus 2. So the first series will be, if n equal to 2, then k will be 0 to infinity. And replace n by k plus 2. So it will be c k plus 2 multiplied by k plus 2 times n minus 1. That will be k minus 1. It is k plus 1 or k plus 1, not minus 1. Just replace n by k plus 2 multiplied by x to power k. For the second one, we'll let k equal to n. No need to change anything for that one. So we'll have sigma k start from 0 to infinity, c k x to power k equal to 0. And we can see k start from 0 and k start from 0 for the two series, and the powers, they are the same. So I can combine the two series in one, sigma, so k equal to 0 to infinity of, I will take x to power k as a common factor. So the first one is c k plus 2 multiplied by k plus 2 times k plus 1 plus ck equal to 0, which means this will give me ck plus 2 multiplied by k plus 2 and k plus 1 plus ck equal to 0, or ck plus 2 equal to ck divided by k plus 2 multiplied by k plus 1. Now for k equal to 0. Let's start with k equal to 0. If k equal to 0, then we will have C2 equal to C0 divided by 2. K equal to 1. I will have C3 equal to C1 divided by 6. Or I can say it is 3 times 2. Only say 2 times 3. Just keep the order. If k equal to 2, I will have C4 equal to C2 divided by 3 times 4. But C2 is given by C1 or C0. So this will be 1 over 2 multiplied by 3 by 4 C0. Again, I know that C2 is given by this relation, 1/2 C0. So C4 is equal to C2. Just replace C2 by 1/2 and times 3 times 4, or 1 over 2 times 3 times 4. 4k equal to 3. Then I will have C5 is equal to C3 divided by 4 multiplied by 5. And this is my relation. So this is 4 times 5. And we know that C3 is given by C1 divided by 2 times 3. So this is equal to 1 over 2 times 3 times 4 times 5 C1. K equal to 4. Just one more. I will have C6 equal to. Then I will have C4 divided by 4 times 5. But we know C4, we go back to see it, to this one. This is 1 over 2, 3, 4. That is 1 over 2, 3, 4 multiplied by, this should be 5 and 6. That's 4, 5, this is 5 and 6. Multiplied by 5 by 6. C0. It means we are going to have the series, if we expanded this one, I will have y can be written as C0 x to power 0 plus C1x plus C2 x square plus C4 or C3 x to power 3 plus C4 x to power 4, and keep going in this way. So this is equal to C0 plus C1x plus C2, which is 1/2. Now I'm going to replace this C2, C3, C4. I know that C2 is equal to 1/2 C0 x to power 2 plus C3. We go back to C3. There's this one. There's 1 over T over 6, or 1 over 2 times 3 C1 x to power 3 plus C4. We found it as 1 over 2, 3, 4 C0. So that is 1 over 2, 3, 4 C0 x to power 4. And keep going in this way. C5 which that will be 1 over 2 times 3 times 4 times 5 C1 x to the power 5 plus C6, which is 1 over 2 times 3 times 4 times 5 times 6 C0 x to the power 6. So if you can think about this, I have C0 there, and C0 and another C0. So if we take C0 as a common factor, we can say that I will have two series. And we can say that y1 equal to C0 multiplied by 1 plus 1 half x squared plus 1 over 2 times 3 x to the power 4 plus 1 over 2 multiplied by 3 by 4 by 5 by 6 x to the power 6. So this is if we take C0 as a common factor. For the second one, if we take C1 as a common factor, so I will have plus, or I can say y2 will be C1 multiplied by x plus 1 over 2 times 3 x to the power 3 plus 1 over 2 3 5 x to the power 5 plus, I keep going in this way. So you can see I have two solutions. Y1 equal to C0, or just what is inside the bracket is 1 plus 1 half x squared plus 1 over 1, 2, 3, 4 x to the power 4, and I have even power. And y2 is the odd power for x. So I have two series, C0 and C1. So these are the two series about the ordinary point x equal to 0. We can write this in compact form for this one also. If you want to write it as in a compact form with sigma, we can do it. So it is, we can say it is x to power 2k where over k factorial. Factorial, that will be k start from 0 to infinity, and y2 will be sigma, where k start from, this time we can say 0 to infinity, but this time it is x to power 2k plus 1. I have odd number divided by 2k plus 1 factorial. So these are the two power series or two solutions for the given differential equation.